Okay, so hello everyone. My name is Al-Moutasem Bellah, and I was one of the presenters for the Pacademia session. And right now, I'm just gonna go through the titration curve just briefly, as I felt I was not clear in the Pacademia session. So let's start. Okay, so let's get some basics down first. We have something called conjugate, base, and pair, and acid. Sorry. Okay, so what are they exactly? So we have, first of all, an acid. What is it? This is a normal acid. It's different from a conjugate base and acid. It accepts a proton. So it donates. It's an acid, so after all, it's of course going to donate. And we have a base that's going to accept. H plus, H plus. Okay? So how is this related to this? So let's take an example for acid like carboxylic acid. We said that it accepts a proton, so it donates, so H plus, and it's going to result in COO minus. Now, this COO minus is what we call a conjugate base. It lost a proton. And for the base, we have an example like NH2. We said bases accept protons, so plus H plus, and we're going to get NH3 plus. This NH3 plus is an acid. Okay? Now, let's go through the structure of the amino acids. COOH, H, NH2, and the R group. Let's focus first of all on the main ones, then we'll go through the R group. Now, at physiological pH, which is between 7.3 and 4, double check on that, but it's in that range. We have the carboxylic acid in its conjugate base form, so CO minus, and the amine group in its conjugate acid. Okay, now you see that we have a 1 positive charge and 1 negative charge, so overall we have a 0 net charge. This is what we call a Zwitter ion. Okay, now Zwitter ion is completely variable. Like there are a lot of it's not really a variable, it's a 0 net charge, but what I'm specifically referring to is the pH at which it is a Zwitter ion. Okay, so the pH at which amino acid is a Zwitter ion is what you call the isoelectric point. Okay, also denoted by PL. Now, the isoelectric point is incredibly variable. Why? Because amino acids have different properties of side chains. You have polar, neutral, polar, sorry, non-polar here. Non-polar, neutral polar, basic, and acidic. Now, these two do not have the capability of having a charge, while acidic and basic can have a charge. So it's going to change the pH at which we get the Zwitter ion. So let's take, for example, the glutamate. Okay, glutamate has an extra carboxylate group in the R group. Okay, so we can see here, first of all, we have something called pK, pKr, pK2 for the amine group, for the R group, and the carboxylic acid group. Okay, so what is it exactly? pK is the pH at which we have 50% of the for example, here we're talking about the carboxylic acid. 50% of it is going to be protonated and the other unprotonated. Okay, so for example, here the pK is 2.19. So anything greater than 2.19 is going to be unprotonated. Anything less than 2.19 is going to be protonated. So let's put this into practice. So here, since the main carboxylic acid group is the strongest, so it has a strong desire to donate a proton, so we require a very high concentration of proton to keep it for itself. So once we decrease the proton concentration or increase the pH, for example, anything greater than 2.19, sorry, like this, 2.19, it's going to lose the charge. Here we get the zero net charge, because here we have a negative charge and a positive charge. So this is what you call a Zwitter ion. Now we have to figure out the pH at which we get this Zwitter ion. But first of all, we need to go through the other species or molecules that could have a charge. So after this, we're going to have the R group of the carboxylic acid of the R group. Again, it's a strong acid. It can donate a proton, so we need a very high concentration of proton and a low pH, so it can maintain it. Okay, so anything greater than 4.25 or pH greater than 4.25, it's gonna lose it. So here we get a negative charge. Now we have two negative charges and a single positive charge, so overall we get a -1. Now we didn't even reach the basic conditions. So once we reach the basic conditions, in which there is very low amount of protons, like anything greater than 9.67, the amine group is also going to lose its proton, hence having a total net charge of -2. Now, how do you find the isoelectric point? We're going to take the division of the R group and the pK1. Okay, why exactly the R group? Because as you can see here, the R group here is protonated. So here is the state where we get a Zwitter ion. So anything in between this pH and this pH, or pK, anything between this pK and this pK is the isoelectric point. So we just simply add them together and divide them. Okay, now let's see if there's a basic example. Just give me a second. So okay, it's not a basic example, but here it's a non-polar or neutral polar example. It's a neutral polar example. Wait, no, it's a non-polar example. Okay, so as you can see here, it's just the average between these two, because here we don't have an R group. We don't have an R group that could have a charge, so we just basically take the average of the pK of the amine group and the acid group, and that's it. So I really hope it's made clear. If you have any questions, please go ahead and just message me on WhatsApp, or even write on the group and just tag me, and inshallah I'll answer any questions you have.